Okay, so today we want to do 4.1 and see how that goes. So this will be on proofs, um, and if you do a lot of math and you keep doing math and you go through the graduate and the undergraduate stuff, eventually you're going to get to um, uh, having to do a lot of proofs. Let me get this thing warmed up. Okay. So maybe not if you do engineering, maybe not so much, but I think there are proofs in some computer science applications when you're trying to figure out how if a program will run given some conditions or something like that. But for most people, you won't have to do proofs. But like I said, if you are a math major, more than likely you're going to have to do proofs. Um, the book will set them up kind of like Mad Libs. It's like basically you're just filling in the blanks, and hopefully you'll appreciate the fact that all proofs kind of have a structure to them, and really all you're doing is kind of filling in the blanks. And for me at least, I leave these sections with the feeling that okay, proofs are kind of almost programmable. If you know the type of proof, you can almost have a computer do it. The computer would just go through and kind of fill in the blanks. At least that's the way I look at it. But for currently, most proofs, I think people would say that computers can't do them. But people used to think that computers couldn't handle chess either, so they were proved wrong. Um, there are a lot of computer proofing programs, but the problem is sometimes the proofs will become so complicated that the human user won't understand why it's true. So that's a real big issue in artificial intelligence. But I don't know. As a student, you wish you could get like a calculator to do the proof for you after a while, because that's all you'll be doing is proof, proof, proof. And classes like abstract algebra, advanced calculus, real analysis, topology, functional analysis, those places, you don't really do numbers very much anymore. You just do proofs. So, anyways, that being said, let's dive in here and whoops, look at 4.1. And what are we working with? This will be about direct proofs. I'm trying to get used to this pen still. Direct proofs. And this is just kind of our introduction to it. So you may think that you already know how to do proofs, like you did proofs in trigonometry and stuff. That's not really what we're talking about here. It's almost some other people think, well, I've done proofs by induction. That's still not exactly what we're talking about here. These direct proofs are kind of like everything that you kind of have internalized. You need to bring that up to a surface and tell people now. For example, uh, if you know that a plus b equals b plus a, can you prove some other facts about is a plus b times c equal to b plus a times c? That sort of thing. I don't know. Anyways, let's get in here and take a look. So there's always going to be basic laws or axioms that you're going to be working with, and these are the basic rules of the class or whatever system you're working in. Okay. Um, we usually generally for us, once you get into a class like abstract algebra, you'll be taking these for granted because you've been working in math systems for so long, everything's been internalized. But in general, you want to know from your teacher what you can use and what you can't use. So can I use, for example, the commutative law? And if you took like linear algebra, you know that that's not always going to work, right? Especially in multiplication. Is the matrix A times B equal to B times A, that sort of thing. But anyways, for us, we have sort of the basic rules listed in Appendix A. And what are these rules? These are the rules like A plus B equals B plus A. Okay. They're the rules that you take for granted. Okay, they're called field axioms. And what is a field? A field is kind of like a where you ended with arithmetic. You can add numbers together, you can multiply numbers, there exists reciprocals and stuff like that. So all those rules bunched together make a field. There's actually, like, if you didn't worry about multiplication, like for some reason you didn't know what multiplication was, like most grade students, you'd be working in something called a group. Okay, so there's groups, then there's rings, then there's fields. And these are all different kinds of algebra systems that are sort of uh, described by the laws that they have. Okay, so in particular, a field will have both a multiplication and an addition property. But very basically, what are they? They're the little rules that we all know and love and take for granted. Like this is, of course, the commutative law of addition. There's a commutative law of multiplication as well. Okay, so the appendix A, you can look back in there. Other stuff, the properties of equality. These guys are also, you're allowed to take these for granted. You can add stuff to both sides of an equation is basically the things that you learned in basic algebra. How do I solve an equation? Well, you can add something to both sides of it. You can multiply something on both sides of it. It's those rules. Okay? You're allowed to do those. If you're ever unsure, you get in a class with like abstract algebra, just ask your teacher, what are the basic laws? What are the basic axioms? Okay? And axioms generally aren't proved, they're just taken for granted. But even in algebra, abstract algebra, you'd be expected to prove simple things like commutative law. I think. It's been a while. Anyways, one extra issue that you may not be familiar with is this idea of closure. And the integers are closed. Okay, which just means that if you add two things together, you're not going to magically get like an irrational number out of it. So if you add like 2 plus 3 together, you're just going to get another integer. Remind yourselves, what are the integer values? Dot dot dot, -2, -1, 0, 1, 2, dot dot dot. Okay. So if you add any two of these together, you're just going to get another number that's in this set. So it's closed under addition, right? But it's also closed under subtraction. And it's even closed under multiplication. And you may say, well, so what? I know that. And it's because it's been beaten into your skull. That's why you know this stuff. It's not always true. For example, if you're working with, you don't want to do that. If you're working with the whole numbers, right? 1, 2, 3, 4, 5, 6, 7 plus 0. If you're working with those numbers and you try to subtract them, you're not going to get, you may not necessarily get another whole number, right? So if you go 5 minus 6, you get -1, which is not a whole number. It's not closed under subtraction. The integers, they're not closed under what? Well, division. Okay. It's like if you have 5 divided by 5, certainly that's 1. That would be another integer, but if you have 5 divided by 3, the division of two integers is, in this case, not going to be another integer, right? It'll pop out into the rationals. The rationals are going to be then closed under everything except limits. Okay, and that's kind of where you would go towards in advanced a class like advanced calculus, which would lead into real analysis. Okay, but anyways, there's that stuff. It's just a lot of stuff you take for granted, and now it's kind of like you have to say it out loud. You're not allowed to no longer sweep it all under the rug, because you'll be working in more abstract systems if you keep doing math. I don't know. Okay, so we're going to have some definitions we want to work with, and the simple kind of proofs, even and odd type proofs. So even odd. And if n is even, if and only if, so one of our biconditional arrows, there exists an integer k such that n is equal to 2 times this particular integer. Okay, n is odd if and only if there exists an integer k, and the integer such that n is equal to 2k plus 1. Okay, so the first kind of intro problems, they'll just want you to note whether or not this given number is even or odd. To show that it's even, there's kind of two things you need to do. First, you need to find this integer, and then you need to show that it's equal to 2 times this integer. Okay, so it's a little awkward. It's not entirely what you think it is. And in the homework, it's pretty easy because all you're doing is filling in blanks. Anyways, the first question is negative 17 odd. So I'll just write odd negative 17. Whoops, not the right 17. There's my 17. Okay. Is that true? It probably is, right? We can write negative 17 as 2 times some. We know it to be true, right? It's not even a matter, is it true? Okay, so we just have to figure out what this integer is that goes in there, right? So what is it, negative 8? And then note that negative 8 is an integer. Okay? So here we note negative 17, and you're writing English, right? So you don't want to just put a bunch of numbers all over the place and expect somebody else to figure it out for you. No, you have to write it in English so other people can appreciate your genius. Okay, so note first off that negative 17 is this. Also, then we need to note that negative 8 is actually in the integers, right? Also, negative 8 is an integer. Hence, it's odd. Okay, so it's 2 times something plus 1, but you have to make sure that that something you're multiplying by is actually an integer. Okay, so let's try another one. Here's one that's always weird. Is 0 even? Well, can you write it as 2 times some integer? Well, yeah. Note 0 is equal to 2 times 0. Also note then 0 is an integer. So what? Well, hence it's 2 times something, where that something is an integer, and therefore it is even. Okay, so 0 is not even or odd. Sorry, 0 is not positive or negative, but it is even. Okay, that's always a little confusing for me, but there it is. Okay, let's look at what is this? This other guy. I think it's part C. Okay, part C. Given k as a particular integer, is 2k minus 1 odd? I'm abbreviating the heck out of that. Okay, sorry if this is just a function such that if you put in this thing, it'll either be true or false, and I'm assuming it's true or false dependent on whether it's odd or even. Right? If it's odd, then putting 2k minus 1 in here will produce a true statement. Okay, so note, in order to show it's odd, we want to write it as 2 times something plus 1, where that something is an integer. So there's those two things. First, you have to note that this 2k minus 1 is equal to 2 times something plus 1. Okay, and to do this, I'm going to have to be a little bit creative. Okay, this is where the creative part of math really pays off. So how can I pull this off? Well, you can go 2k plus 2 and then minus 1, right? And that's the same thing, right? Well, it's not exactly the same thing, Dave. It's a little bit different. So I screwed that up a little bit, but we can fix it, right? You have to have it work for our means. I need this part to be positive 1, right? So hey, let's make this negative, and then this will be plus 1. They're equivalent, right? Negative 2 plus 1 is just negative 1. But now I have it in this form where it's something plus 1. More to the point, I need 2 times something plus 1, but that's okay because we can factor out a 2. So this would be 2 times k minus 1 plus 1. Okay, so that's our first thing to notice. And then also note k minus 1 is a difference of integers. Yeah, I keep hitting the little button, sorry. Difference of integers, and therefore an integer, because the integers are closed under subtraction. Okay, so we have it, right? So thus, hence, 2k minus 1 is odd. Okay. So this function would spit back a true. Okay, let's get some more definitions into the mix here. So the next definition is prime and composite. Sorry. Okay, so n is prime. If and only if, what? For all positive integers, I'll just write it out. Positive integers R and S. If n is equal to R times S, we need to make sure that neither one of these is 1, right? Sorry, we need them. That's the composite definition. We need to make sure that one of these has to be 1. Okay, so if n is equal to R times S, then there's 2 possible cases. Either R is equal to 1 and n is equal to S, or S is equal to 1 and R is equal to n. Okay. The other one then for composite, and it is composite, if and only if there exists a positive integer, I'll just abbreviate those, sorry about that if you hate that, you can write it all out if you want, R and S, such that n equals R times S, and R and S are greater than 1, right? So R is greater than 1 but less than n, and S is the same, right? Okay, so we want to play around with proofs based off of working with these definitions. Okay, so let's look at number 4. And we'll assume R and S are integers, particular integers. Okay, we'll presume that integers exist. And let's look at part C. Okay. So part C is asking if R and S are both positives, is the following composite. So if R and S are positive, then is this polynomial r squared plus 2rs plus s squared composite. Okay. So what I'm going to first do is call this thing something. So I'm going to kind of instantiate it, right? So bring it into existence. We'll say let n equal r squared plus 2rs plus s squared. And then use some algebra to note. So I'm noting the following. R squared plus 2rs plus s is equal to r plus s times r plus s. Okay. Then you can note this one maybe it's the obvious things that we take for granted. So one obvious thing is this. Note because r and s are positive integers, so because r and s are positive integers, that means both of them are greater than or equal to 1. And then if you add these two together, that's definitely got to be greater than 1. Okay, so the smallest r can be is 1, the smallest s can be is 1. And the kind of argument that I'm putting forth is something I should really be writing down. Anything you sort of think in your head as the kind of, I mean, I wouldn't expect you to, and on the software all you're doing is filling in the blanks, but eventually you would have to write your own proofs. That would be the end goal. And one thing that I always took for granted is all that sort of justification that you're thinking in your head for why this is true and why you need to kind of inflate that during your proofs. You need to write all that junk out and make sure it all works. So anyways, note because r and s are positive integers, this has to be true. R plus s has to be greater than 1. Then by axioms, order axioms, so that means basically the inequality facts. So then by inequality axioms, which are listed in that Appendix A, you can multiply both sides by r plus s of this inequality, and what do you get? Well, you get something that connects us to this guy back here, right? Okay, so in particular, you could say that this r plus s squared, in other words, this guy right here, is going to be greater than 1. And that's we're kind of after that definition for composites, right? So we need these two things to be greater than 1 but less than n. Okay? Where it's a little confusing because now we have n is defined as something else. If you do computer programming, you got to be a little bit careful about how you define your variables in certain places, right? So it's a little like that. Anyways, here we have our inequality formed. R plus s is just r plus n squared is just n, and so I think hopefully it's kind of clear. Thus, we can kind of say that this r plus s thing is in between 1 and n. Okay, so that just is kind of the transitive property of inequalities, right? So if this is less than this and this is less than this, then this guy here is less than this guy here. Okay, which is just n. Does that make sense? So I can put all these together, I guess, is what I'm trying to say, and have this final inequality. So thus, by the transitive property this final inequality is true, which will hold for both factors of r plus s, which means the thing is composite. Okay. Hence, by definition, n is composite. Okay, so one thing to note about this proof, it's probably, all right, well, that's great. How would I do this? If I'm not really good at proofs, or whatever. Well, the truth is, this is not my first try at this proof, right? I've done it before. When I first approached it, I probably, would literally just kind of throw a bunch of stuff at a wall and work with it a little bit and kind of get the functionality of the whole deal. And then I'm kind of trying to match to the definition the things I need. So I'm trying to build the kind of the definition of a composite through all of this work, using my knowledge of algebra and all the little axioms that we kind of take for granted, right? So when I do a proof, generally I'll have a skeleton which will look a lot like those propositional arguments. I'll just start labeling facts, and then it just turns into kind of a puzzle where all you're doing is connecting fact to fact to fact, using algebra or axioms or definitions, what have you. Okay. Fortunately for us, for now, in the homework, it's just going to be fill in the blanks. Okay. Okay. Let me cut the video short here, and then we'll start in with the other stuff in the next one. I don't want to make my videos too long. I'm using this new software. Okay. Okay. So I'll see you in the next video.